That's great. Yeah, thank you. Right, so I will be talking about sort of some of the physical systems which realize some of these sort of quantum cellular automata and related structures. I'm not going to be talking about sort of very specific sort of materials or anything like that. I'm just going to be talking about sort of general physical contexts in which some of these classifications are applicable. If you're a mathematician, you just might not care. About the sort of physical context in which various things arise. I mean, you might just be happy with the classification problem, solve classification problem. But in that case, you can just kind of think of this as story time. Okay, good. Okay, all right. Good. So let me sort of take a step back and kind of have a big picture view of how what do you mean by phases of matter? All the things that we heard yesterday, for instance, about modular tensor categories and sort of sophisticated math. In what context is that math realized physically? For the most part, most of these mathematical structures relate to zero temperature equilibrium phases of quantum matter. Okay, so the idea is that you have some kind of a many-body system, and you can really think about a lattice, think about qubits on a lattice, it's a many-qubit system with some kind of a local Hamiltonian. For the most part, here we think about gapped Hamiltonians, and then all the sort of fancy math with the unitary modular tensor categories and all this stuff really relates to sort of describing the properties of the ground state of such a local gapped Hamiltonian. It's really just physics of the ground state, maybe with some excitations on top of it. Maybe some finite number of excitations on top of it. But it's really basically at zero energy. Okay, zero energy plus a few finite excitations. It's not at finite energy density. It's at zero energy. So physically, the way that you would engineer such things is you take a quantum many-body system and you cool it to zero temperature. If you think about sort of systems at finite temperature, there's sort of a Boltzmann weight which tells you sort of the probability of being in various energy eigenstates at zero temperature. All that weight is concentrated on the ground state, and it's just physics of the ground state. Okay, so we're really talking about zero temperature equilibrium phases of quantum matter. When I say zero temperature, I said temperature, so by definition, equilibrium. And so, in some very coarse way, if you just sort of imagine a caricature of the space of all gapped Hamiltonians. So here, again, I'm sort of suppressing all possible details. You can have in your mind, some kind of a lattice system in the infinite thermodynamic infinite volume limit. And the space of Hamiltonians could be sort of parametrized by the values of the various coupling constants of the various terms that you can write down. So it's some horrible, infinite dimensional space. I'm not going to try to formalize it at all. I'm just going to sort of put up this crude caricature, which sort of tells you about what it is you're trying to do. So roughly speaking, the idea is that you have this space of all Hamiltonians. Let's pretend we're working in 2 dimensions. So all 2-dimensional Hamiltonians. And then within that space of all Hamiltonians, you have gapped Hamiltonians. Okay, and so the basic idea, again, at the level of this caricature, is that different topological phases, which support different anyons described by different, let's say, unitary modular tensor categories, correspond to somehow different connected components of this space of all Hamiltonians. Okay, so this is kind of a nice, again, I'm not formalizing anything, none of this is sort of remotely rigorous, but this is just a nice kind of picture to have in your mind. Okay, so these connected components we refer to as different zero temperature phases of matter, and so the reason for that is if you were to imagine starting out in one of these connected components, so that corresponds to one particular gapped Hamiltonian, and then continuously varying parameters to end up in a different connected component, you have to go through a phase transition. You somehow can't stay within the space of all gapped Hamiltonians. You have to leave the space of gapped Hamiltonians. The gap closes. And correspondingly, there's some non-analyticities in various observables like ground state energy or something like that. Okay, so that's sort of what this math of unitary modular tensor categories relates to. It's the space of all gapped Hamiltonians. Now, as far as sort of practicalities in physics, I want to just emphasize that these are very difficult to actually engineer in practice. I mean, what's your system of what are your quantum degrees of freedom going to be? For the most part, in condensed matter, we deal with electronic degrees of freedom. So we deal with electrons moving in the background of some crystalline lattice of ions. Your degrees of freedom are electrons. And it's actually very hard, even if sort of in principle you can write down various gapped Hamiltonians realizing all sorts of exotic topological phases, in practice it's very hard to actually engineer systems that realize those phases. I mean, you don't have a lot of control over materials. Like, it just kind of is what it is. It's gallium arsenide. It has a certain lattice structure. And you don't have a lot of tuning parameters. You have some tuning parameters. You can sort of apply pressure. You do different things, but you don't have a lot of tuning parameters. So it's difficult to sort of realize topological phases. And since the 1980s, when the fractional quantum Hall effect was discovered, which realizes these topological phases, basically the only material in which, I mean, it's not really material, it's sort of an engineered heterostructure, but the only setting in which you can realize is these really these quantum well heterostructures where you trap a two-dimensional electron gas, sort of effectively confine it in one dimension, so it's a two-dimensional electron gas, you apply a magnetic field, and that turns out to be sort of just the right set of ingredients for realizing these exotic Hamiltonians. But this is hard, there's very low temperatures. You need a dilution refrigerator. There's all sorts of problems. I mean, disorder, just in general in solid state systems, there's, in addition to electrons, there's other degrees of freedom, there's lattice vibrations. It's very difficult to sort of, work with these things. And so, so it's nice to sort of at least look for other settings, physically other settings in which you can realize some of these sort of exotic phenomena, topological phases, or maybe some kind of exotic Hamiltonians that relate to topology. And so let me just sort of mention again at the level of pictures some of the sort of new quantum many-body systems which aren't really sort of part of the traditional solid state systems which have become prominent recently. So one set of many-body quantum systems that people have really made a lot of progress on is ultra-cold atoms trapped in optical lattices. Okay, so it's a completely different setting from electrons in an ionic crystal lattice. The degrees of freedom here are atoms; they're much heavier. So it's sort of maybe harder to make them quantum. You have to go to lower temperatures, but there's a lot of advantages to these kinds of cold atoms in optical lattices. So, for instance, these new systems, sort of eliminate disorder, as opposed to like a lattice of ions where you can have sort of weird disorder. An optical lattice is just made out of interfering lasers, and that's not going to have any disorder. These things are tunable. You can sort of tune the strength of the laser, tune the strength of these potentials. You can sort of, some nice tuning parameters. And in fact, you can realize, it was pretty early on, the people saw you could realize a mod insulator superfluid transition in this kind of setting. So these are sort of have a lot of promise for many-body quantum phases. There's no extraneous degrees of freedom, no phonons, no lattice vibrations. So these nice isolated quantum systems. Similarly trapped ions, another similar setting. But there is sort of one very big problem with these kinds of new designer quantum systems. And it's sort of the flip side of the fact that they're very clean and isolated. It's hard to cool them down to the ground state. If they're isolated and aren't really coupled well to the environment, it just means they're hard to cool down. You need coupling to environments to sort of take away the energy and cool the system down to a ground state. So many advantages to these sort of new kinds of platforms, but one disadvantage is just hard to reach the ground state, and that's bad, from the perspective of what I told you, because these topological phases, they're physics of the ground state, and if you can't reach the ground state, then what do you have? So Okay, so that's one sort of new physical setting. Another new sort of physical idea is to sort of go beyond static Hamiltonian. So this is sort of just adding another knob to the systems that you're looking at. And this can be sort of realized both in the sort of original solid state context, electrons, crystalline lattices, as well as these new optical lattice systems or whatever. And this is just the idea of adding a Floquet drive. Floquet is just a fancy word for time periodic. So it's just adding a perturbation to the Hamiltonian, which is periodic in time. Okay, so that's just another knob that you can turn on. And why would you want to do this? Well, it turns out that at least at the level of sort of free fermion band structures, again, this is not going to be important for the rest of what I talk about, so I'm not going to sort of formally define a free fermion band structure. If you know what it is, great. If not, it's going to be okay. But sort of at the level of free fermion band structures, it was sort of realized that this kind of periodic Floquet drive is nice because it allows you to sort of create band structures which have, for instance, Chern number or some other non-trivial topological properties out of topologically trivial ones. So that's kind of cool. I mean, it's another way to realize topology. And so, okay, so that's another ingredient that we can consider. Yep.
Proposals remotely practical? I mean, you're shining all this high frequency light on the system.
Yeah.
You want too much ground state.
Well, okay, just hold on 2 slides. You'll see. I'll get to that.
Very quickly. So, is any relevant, like if I can think of those systems as symmetry breaking from the real life to the integers for the time variable?
Yeah, I mean, so answering that question would require me to introduce some of these concepts like MBL and things. So let me wait.
It's not completely wrong.
It's not completely wrong, but yeah, I'm sort of slowly setting the stage. I sort of set these things up. Now I'm going to tell you what the problems with them are, and then we'll go from there. So regarding these Floquet systems, sort of related to what Mike just asked, how do you realize a Floquet drive? Like you can shine a laser on your material. That's sort of a periodic in time perturbation. But sort of Mike alluded to, there's problems with, sort of at a naive level, yeah, you have these maybe topologically non-trivial band structures in these Floquet systems, but if you think a little more about it, it's not really clear what that means. So like first of all, for a Floquet-driven system, it really makes no sense to think about diagonalizing a Hamiltonian at instantaneous value of time. That doesn't really tell you anything about the physics. Instead, it turns out, and I'll sort of refer back to this later, it's useful to consider this Floquet unitary, which is sort of the time evolution over a single period. It turns out that diagonalizing that operator tells you something about sort of long time behavior, at least sort of these stroboscopic times, integer multiples of the period. But this is a unitary. So at the level of free fermions, you diagonalize this thing, you get eigenvalues that sit on the unit circle in the complex plane. So there isn't a lowest, there is no notion of like low energy states. There's no notion of a ground state that you can obtain by filling states below a certain energy. So sort of just at a formal level, doesn't it's sort of difficult to make sense of. And in fact, there's a sort of a greater problem if you think about the fact that that free fermions are never sort of the ultimate description of the system. There's always some kind of interactions between the electrons, and it's just sort of a general fact that when you have, and again, I'll formalize this in a moment, but it's a general fact when you have interacting many-body system and you sort of put in a perturbation to it like a laser, time-dependent perturbation, that tends to just dump energy into the system. Okay, so this is known as the heating problem, and the heating problem can be described as this. This works better if I flip through the slides, not in a PDF. I think that's the heating problem. It's bad for realizing you're definitely not in the ground state here. So, okay, so we have. Yes, it's a warming problem. That's right. Okay, so nevertheless, it turns out that recently people have found, at least sort of at a conceptual level, ways around these heating problems. So basically there's sort of 2 problems. In the time-independent case, difficulty of cooling down to the ground state, And the time-dependent case is just this heating problem that, you just keep absorbing energy until you blow up. So there are ways to work around that, but before I'm going to describe that. That's going to be sort of the bulk of this this lecture. That turns out to relate to QCAs. Before I describe the solution, let me just formalize these heating problem, the notion of this heating problem. So to do that, let me switch back to, hopefully this will work. Switch back to writing. So let me formalize some of these problems. So the general idea that formalizes these problems is something known as the Eigenstate thermalization hypothesis. Or it should really be called Eigenstate thermalization property. It's a property that a lot of systems have. It's a property that most systems have. It's a property that's very hard to evade. But if you can evade it, then you can get around some of these problems, heating problems. Okay, so this is ETH, abbreviated ETH. So let me first start talking about time-independent Hamiltonian. Okay, whoa, what's going on? Okay, so I have time-independent Hamiltonian. So time-independent Hamiltonian H. And let me imagine that I have a state. Okay, so let me first maybe draw a picture of the system. The system looks like this. Let's say it's some volume V, so there's like V qubits in here. That's sort of my caricature. Okay, and they could be fermions, but I'm just going to do qubits for simplicity, bosonic degrees of freedom. There's some Hamiltonian that makes them interact. So, just for simplicity, I'm going to say that the ground state is at energy 0. So the ground state is, I'm just going to just set that to be at energy 0, so that's the ground state. That's sort of the lowest available energy. The maximum energy in this kind of a system, well, it is whatever the maximal eigenvalue of the Hamiltonian is, but it's going to scale. For a local Hamiltonian, it's going to scale roughly like the number of qubits. So the maximum eigenvalue is out here, and it's like E max, which goes like some energy scale J times the number of qubits. Okay, so that's sort of the energy scales we're talking about. And so what I want to do is I want to consider a state now. Remember, we're trying to sort of address this cooling problem. So we have a state that we're having a hard time cooling down to the ground state. So let's say we have a state somewhere in the middle of this spectrum. It's at finite energy density. Okay, so it's some order 1 fraction of J times V. Okay, so let me call that state psi of 0. So psi of 0. 0 is going to denote time, so I'm starting at time 0. And the expectation value of the energy for this state is equal to, some fraction J prime times V. Okay, so this is less than JV. Okay. I'm implicitly working in sort of a large V limit. There's some limits V going to infinity, which I'm implicitly taking here. So one thing that we know about this immediately is that since energy is a conserved quantity, at any subsequent time, if I just evolve psi according to the Schrodinger equation, which I'm not writing out, that energy is maintained. This might not be a stationary state, but at least the energy is conserved, so the energy stays the same. So it just sits at finite energy density. Okay, so what does the eigenstate thermalization hypothesis say about such a state? I mean, there's various ways to formulate it, but I'm just going to formulate it in a way that's convenient for me. So what it says is it's a statement that relates to sort of reduced density matrices of psi of t. It sort of tells you how reduced density matrices of psi of t evolve in time. Psi of t is a pure state. It evolves in some complicated way. It's not necessarily an eigenstate. It's some state of finite energy density. So it has this expectation value. It could be a superposition of eigenstates. It evolves in some complicated way. Eigenstate thermalization hypothesis tells you about the evolution of, if you just look at the reduced density matrices of the state on sort of small regions. And I'm going to be vague about what I mean by small, some small fraction of V, let's say. It could be order 1. I think it's like works up to a half or something, but you know, let's just take a tenth or something. So basically, ETH is the statement, or the ETH property is that this reduced density matrix. So let me define reduced density matrix. Reduced density matrix on A at time t is, trace out it's the usual definition, trace out the complement of A from this mixed state. Okay, so you construct the density operator for this pure state, and you trace out the complement of this finite region. That's now some mixed state. And what the ETH says is that in time, rho A of t looks like a thermal state. So rho A of t approaches something that looks like a thermal state. So up to a normalization, trace of this thing has to be 1. This looks like the trace of a thermal state, e to the minus h over kt, for some temperature t. So there exists some temperature t, okay? There exists some temperature t for which the thermal state, this e to the minus h over kt, it's a mixed state on the full system, looks like rho A of t in the infinite time limit. Okay, so it just says that even though it's a pure state, it begins to look thermal on small subsystems. And t, the temperature t, is determined uniquely by the fact that the expectation value of the energy in this on the right-hand side better be equal to whatever j prime times z. Yeah. Either one. Matt.
So quick question. I thought maybe there's different things called eigenstate thermalization. I thought it was that if it's an eigenstate, then it's
so that would be implied by this,
Right. So is this but this is sort of at the same status?
This is the same status. Yeah, I think these are all. You can show these are equivalent.
And you're saying that it really should be true for any given t as t gets large, with the system size being taken larger first. You don't need to average over t.
Yeah, you don't need to average over t. That's right.
For any specific t, as long as t is large, but the system size is larger first, so there's no recurrence.
I think so. Yeah, I'm not 100% sure about the technicalities, but yeah, I mean, all I'll need is a rough statement.
I guess my question is actually pretty similar. So
Okay.
if you added like a correction, like a 1 over temperature, or sorry, 1 over time or something, is that correction universal, or is that not expected?
The corrections to this?
Yeah, with long time.
No reason to suspect that they would be. Not sure. It's a good question. Maybe this is something that's sort of well known in the ETH community.
Actually, it's a little bit known. It's related to a specific hit.
Oh, okay.
Yeah, there are at least the lowest order correction.
But in any case, I'm going to. The rest of my talk is going to be about violating this. So I'm going to very strongly violate this. Yeah.
Yeah, I just want to know what is the hypothesis. So the hypothesis is always true, or
Yeah, the hypothesis is just the wrong word here. I don't know why people use hypothesis. It's a property. So it's some systems have this property, some systems don't.
What I mean is, as a mathematician, when you say some hypothesis, that means that every system behaves.
I know. I'm saying that the hypothesis is the wrong word here. It's just historical artifact. That's why it's stuck.
If you might try to prove that it's true for like a measure, for a full measure subset of translation variance in channel.
Right. Yeah. So I'll show you. It should really be called eigenstate thermalization property, and I'll show you ways to evade this.
That also, I would say, call it ET,
Yeah. I didn't make up the name. Okay, so this is for the case of time-independent systems. Let me just briefly mention what happens for the case of time-dependent systems. It's the exact same sort of setup. I'll start with an initial state. It's not going to have a fixed energy density in time now because there's no conserved energy for the evolution. So ETH is actually simpler for the case of Floquet-driven systems. Floquet. For the case of Floquet-driven systems, the claim is that, what can this possibly be? Well, it goes to an infinite temperature state. Infinite temperature state just means, the infinite temperature Gibbs state is just the identity matrix up to normalization. So this is, 1 over whatever, just the identity. It goes to the identity. Just infinite temperature. It blows up. Dump too much energy into it. Okay, so this is sort of bad from the perspective of trying to realize, let's say, topological phases, things like this, because those are really sort of strictly zero temperature phases. If you look at finite temperature states, finite temperature Gibbs states, at least in 2D, there should be no phase transition. Somehow, all the topological order for systems which satisfy ETH, somehow all the topological order, all this sort of fun stuff that we have kind of gets washed out. These thermal states just, there aren't, they're conjectured not to be finite temperature phases here. The topological phases are, in 2D at least, are strictly at zero temperature. So this is sort of bad from the perspective of topological order. I mean, you can kind of sort of an intuitive level in the Floquet case, obviously, like the thing just blows up. That's obviously bad for realizing some delicate ordered state. So this is bad. So now let me tell you about, yeah.
Are you saying that for any system that has the ETH property, when you drive it periodically, you get this Floquet rho AMT?
Yeah, so the statement of the ETH property for systems which are periodically driven is this. And it turns out that, for a long time it was just thought that generically, like, this should just always be true. Like, it was thought that systems just thermalize in this way. Now, obviously, you can build specific Hamiltonians which don't have this property. They're integrable systems that have a lot of conserved quantities that do not thermalize in this way. They have local. You can build pathological examples of Hamiltonians, obviously, that don't do this, like it's completely decoupled blocks or something like that. But it was believed that these things are sort of very fragile. They're fragile to perturbation. And so one of the big developments in the last decade or so is that there's a generic exception to this ETH. So in other words, there are examples, and these are many-body-localized Hamiltonians, which not only violate ETH, but in a robust way, in a way that's stable to perturbation. So I listed some of the references for MBL, many-body-localization, on that board. There's a long history. There is sort of even a mathematical proof for a certain system with a certain perturbation. So, but in general, this is sort of a numerically driven subject. So just sort of keep that in mind. Let me sort of just describe the essence of this idea of many-body localization. Okay, and let me start by talking about the time-independent case. There's a time-dependent Floquet version, and there's a time-independent version. Let me see how much time I have. Okay. In the time-independent case, let me first start out with the following Hamiltonian. So let me start out with a Hamiltonian, which I'll call H, which will be, let's say that I'm in 1D here. This stuff does generalize to higher dimensions, but there are subtleties with many-body localization in higher dimensions. I don't want to get into any of that, so I'm just going to, for now, stick to one dimension. And let me just consider a simple Hamiltonian on qubits in a one-dimensional spin chain, which is just something like, maybe sum of h times z. So this is Pauli z over all sites I. Let me start out with this really dumb Hamiltonian. Okay, so this is a decoupled spins, and obviously this kind of Hamiltonian doesn't satisfy this eigenstate thermalization hypothesis. The dynamics in this Hamiltonian is completely trivial. You start in a state in the computational basis, you just stay there. Nothing happens. You're not gonna thermalize. One way that this can be formalized is that this Hamiltonian has many local conserved quantities. Okay, each Pauli z at each site is an operator that commutes with the Hamiltonian. It's a conserved quantity. So at an intuitive level, if you have many local conserved quantities, the thing just doesn't thermalize because thermalization requires energy to sort of be dispersed everywhere. So this is a Hamiltonian that sort of does technically evade ETH, but at least if I keep this coupling constant h fixed, I can sort of immediately break this property of local conserved quantities by introducing a perturbation. We call it epsilon times xi plus 1. So this couples neighboring spins. So this is a very simple chain. This is actually This is exactly solvable. This is secretly free fermions via Jordan-Wigner transformation. This particular system, you can just exactly solve and see that it has no local conserved quantities. This is in the sort of fermionic language, this is like having fermions which have some dispersion. And so, free fermions with a dispersion sort of should be diagonalized in reciprocal space. And so sort of the conserved quantities are occupation numbers of reciprocal space modes, but there are no real space local conserved quantities. There are conserved quantities in this, but they're not real space conserved quantities. So you can sort of see that this idea, at least of having real space conserved quantities goes away for this kind of dumb system when you turn on this perturbation. But now let me now take a slightly different Hamiltonian. Let me take a Hamiltonian which I'll call H prime, which is this Hamiltonian, but I'm going to disorder the couplings. So I'm going to maybe draw these couplings HI from some random distribution. And then just for the heck of it, I'm just going to add terms Jij, Zi, Zj, where Jij is some short-range coupling as well, so maybe just nearest neighbor. And again, Hi and Jij are drawn from some disordered distribution. So it's a random Hamiltonian. So in this case, well, again, I have local conserved quantities. I have every Zi commutes with the evolution here. Again, this is just kind of eigenstates or states in the computational basis. But now it turns out that this is believed to be robust. Well, okay, so there's actually, I think for this particular case, there's a proof, but there's sort of a more general statement where it's just kind of a belief that this is robust to adding in perturbation. So for instance, now if I add in this perturbation, okay, let me actually write a new Hamiltonian H double prime, which is these two terms, plus some, the same perturbation which doesn't commute with these local conserved quantities. Xi plus 1. Okay, so now I added in this perturbation. So remember, when I had uniform couplings, this original Hamiltonian H, that broke everything. It got rid of all our local conserved quantities. The statement now, though, is that with these disordered couplings with sufficient disorder strength, it turns out that you still have local conserved quantities even if you're perturbed in this way. That's sort of the essence of many-body localization. So formally speaking, there exists a finite depth circuit let me call it U, such that such that I can conjugate H double prime, this perturbed Hamiltonian, by U, and get a Hamiltonian that's of the original H prime form. So get a Hamiltonian, maybe with some new values of these couplings. I'm sort of using primes in an inconsistent way here, but that's okay. Sum over I, this is sum over ij, jij, prime, zi, zj. Okay, so what this means is that the zi's, which are local operators, commute with this conjugated version of H double prime, which means that if you sort of instead conjugate the zi, it means that these quantities u times zi times u dagger, these are local conserved quantities for H double prime. Okay, so H double prime has local conserved quantities. They're maybe spread out a little bit, and how much they're spread out, the depth of the circuit depends on the perturbation that you add. But the idea is that there is this stability to perturbations. Okay, again, this is sort of there's only a mathematical proof in a very limited context of sort of the limit of very large disorder for a certain 1D spin chain, but it's sort of based on numerical experiment believed to be a sort of general property. Okay, so so this is the many-body localization, the MBL property for at least for one-dimensional systems. You can play the same kinds of games in higher dimensions. There are subtleties in higher dimensions that I'm not going to get into regarding disorder. Any questions at this point?
Just a reference question. So
Yes.
the proof you referred to is it's like John something, right? The mathematical proof.
Oh, yeah, so I have the reference there, John Embry.
Yeah.
Yeah. Okay. And okay, so now let me also mention sort of the Floquet version of this. So it turns out that you know, this kind of robustness, this existence of local conserved quantities that are robust to perturbations, can also be robust to periodic drives. Okay, so in this case, in the case of Floquet systems, you have to be, you know, you have to say it slightly differently, since in the case of Floquet, yeah.
How much of this depends on the kind of disorder you have?
It doesn't depend much on the kind. It depends. It has to be strong enough, and in fact, it doesn't really have to be disorder. It could be you know, a quasi-periodic potential that's sort of incommensurate with you know, imagine that you have a system on a lattice and you put in a sine wave perturbation that's a wavelength that's incommensurate with the lattice. That will work just as well. The key idea is just kind of to get rid of these sort of, get great translational invariance in some very robust way. Yeah. So in the case of the Floquet systems, it turns out that there's a yeah. So it turns out that MBL can also be robust, and there are examples of this. Here you have to formulate this property as a property not of the sort of instantaneous Hamiltonian, which you know, again, doesn't really, diagonalizing that doesn't really tell you about anything about long-time dynamics, but rather in terms of this Floquet unitary. So remember, we had this Floquet unitary, which is just time evolution over a single period. So it's time-ordered exponential of you know, of the evolution over a single period. So it turns out that you know, there's something called Floquet's theorem, which tells you that, you know, if you diagonalize this Floquet unitary, that basically tells you everything you need to know about you know, solutions of this time-dependent Schrodinger equation. So the name of the game is to just diagonalize this Floquet unitary, and the MBL property in the context of Floquet systems is a property that relates to the form of this Floquet unitary. It's basically that the Floquet unitary has the form e to the minus it times HMBL, where HMBL is precisely something of, you know, of this form here that has this MBL property. Okay. So in other words, HMBL has lots of local conserved quantities, and the Floquet unitary is the, you know, finite time is equal to just the exponential of that over a single period. So the Floquet unitary itself, therefore, also has these local conserved quantities. Okay. So right. So that's sort of a lot of technicalities. Let me sort of step back again and just sort of tell you about how this relates to you know, sort of the problems that I set out initially. So yeah.
I just wanted to ask, when you talked about the perturbation, I think you said it had to be strong enough. Did you mean weak enough?
Sorry, the disorder has to be strong enough. The perturbation is...
The disorder is the xi plus 1 term?
Yes.
The top
No, sorry. The disorder is just you know, the fact that these coefficients hi prime and j prime are vary from site to site.
Oh, I see. But,
Yeah.
but the statement is that the perturbation term with the non-commuting,
Yeah.
that should be small.
Well, sorry, it's a relative statement, right? Because there's you know, you're comparing energy scales.
Yes.
So
With respect to the variance of the j's.
Yeah. Shit, am I saying that wrong? Yeah, I mean, basically the perturbation has to be small. The you know, the disorder term has to be large. I can, you know, give me a couple more minutes. I can probably come up with a more formal statement. Yeah. Okay. So, but yeah. So let me sort of step back and you know, tell you how this relates to sort of this problem that I set out initially of realizing topological order in sort of maybe a more general context. So so the idea is really that this MBL property is a property that protects protects quantum information, protects topological order. It's sort of very analogous to the gap property in equilibrium. The gap property, the gap is somehow the thing that protects the topological and the ground state. You put on a perturbation, as long as the gap remains, you're in this sort of same order phase. The MBL property kind of plays the same role here, and so so the idea is that for instance, if you're working with time-independent Hamiltonians, but you can't reach the ground state, for instance, for instance, in these optical ultra-cold atoms in optical lattices. Okay, so you can't reach the ground state, but if you can engineer a many-body-localized Hamiltonian, which isn't actually preposterous. I mean, you can engineer these kinds of non-translationally invariant systems by sort of shining lasers in various incommensurate ways onto the lattice. So if you can engineer such many-body-localized Hamiltonians, then things might be kind of nice because for instance, you can imagine, let's say, if you're in 2 dimensions. Let's say, I mean, this is just sort of at a theoretical level. Let's say that you're trying to engineer toric code topological order. So toric code, we all know the toric code Hamiltonian. There are these star terms, there are these vertex terms, and the toric code Hamiltonian is, it's a very nice Hamiltonian. These star and vertex terms all commute with each other. They're all therefore conserved quantities of the Hamiltonian. So it's sort of very analogous to this 1D spin chain situation that I was talking about. So if you take this toric code Hamiltonian with all the same couplings, that Hamiltonian does have it's not just the ground state which has this topological order. There's a basis of eigenstates which all have this topological order. But just as in this 1D translation invariant example, that's believed to be ruined at finite energy density by turning on perturbation. So if you turn on some kind of perturbation to the toric code, this translationally invariant toric code, your ground state will still be topological order. That's sort of protected by the gap, but the excited state spectrum, all hell might break loose. Like you just, and in general, you sort of expect this ETH property. So, however, if you start with disordered couplings, so if you just take the toric code but disorder all the vertex and plaquette terms, just their coefficients be random, again, that has a basis of eigenstates where all these eigenstates are area law entangled eigenstates. They all look like the toric code ground state, except that the eigenvalues of some of the plaquettes or some of the vertices might be flipped. But now that property turns out to be robust to perturbation. Okay, so this is sort of the essence of trying to, I could sort of try to formalize this more, but this is sort of the essence of trying to realize topological order at finite energy density. It's not just the ground state now that has this sort of nice area law topologically ordered that does this topologically ordered state. It's the entire spectrum. Okay, so now you can sort of hope to maybe see something at finite energy density. So that's sort of the idea. Similarly, in the case of Floquet-driven systems, same kind of idea. So in the case of Floquet-driven systems, if I think about Floquet-driven systems, so Floquet-driven systems. Okay, so this is sort of some caricature of the space of all Floquet-driven systems. Most of them, well, not necessarily most of them, but the ones that satisfy this ETH property, they're not particularly interesting at large time. They just keep absorbing energy until they blow up, and you don't see anything. But you can imagine that there's these sort of islands. There's these robust, sets, not just sets of measure 0, but sets of some finite measure, which have the MBL property. And you can imagine that maybe there's sort of many different ones, Okay, so I phrased this MBL property in terms of a particular set of local conserved quantities in the context of this one-dimensional spin chain, which were just Pauli Z's on site. That's sort of a boring set of maybe a boring set of conserved quantities, but you can imagine more interesting sets of conserved quantities, such as these toric code vertex and plaquette terms. So I already mentioned this in the time-independent context. You can maybe realize sort of different topological orders in finite energy density eigenstates. In the case of Floquet systems, in the case of Floquet systems where the Floquet unitary is e to the I-t of this form, again, a similar thing obviously might happen. You might realize topological order in eigenstates of these HMBL and eigenstates of this effective MBL Hamiltonian. But it turns out that there's actually sort of a much richer set of phenomena that can occur in these Floquet-driven systems. There's more that can happen. Okay, so that's actually one of the things that makes Floquet-driven systems with this MBL property nice. It turns out that you can realize phenomena. So in other words, there are Floquet MBL phases. These connected components are called Floquet MBL phases, which realize sort of quantized invariants, realize sort of edge phenomena, various things of a topological nature, which have no equilibrium counterpart. It's not like realizing topological order in eigenstates of a time-independent Hamiltonian. There's more, basically. Okay, so there's some references for this that I put up there. Floquet MBL SPD is by Elsa and Nayak, Shabadi Sandi, Kurt von Kaiserling, and collaborators as of, this was like 5-6 years ago. And this is really an incomplete story even as of now, sort of classifying Floquet MBL phases. You can classify, you can sort of run the same classification program that you do in equilibrium. Imagine adding symmetries, imagine considering fermions, all sorts of things. And this is really largely an incomplete program, but at least there's sort of a program. There's an idea of using the MBL as a tool to protect topological order in these Floquet-driven systems. So these Floquet MBL phases do not absorb energy from the drive. They're sort of protected. There's just not enough resonances for these things to absorb energy from the drive. And so, so I was going to show an example of this, which will relate to what Matt talked about. It turns out that there's an example. This is my work with collaborators from 2016. The references up there. Examples of such phases in 2D. So these are called 2D MBL chiral Floquet phases. Which have no equilibrium counterpart. So this is an example of phases with no equilibrium counterpart, and these are sort of simple because there's no symmetries involved here either. These are rather simple phases, but it turns out that they have no equilibrium counterpart. So since I have 10 minutes, perhaps I'll just start talking about this here, and then we'll see how far I get, and you can always ask me over lunch, or I can sort of mention it later. So I'm just trying to decide what I can do exactly in 10 minutes. Okay, let me at least set things up, and hopefully Matt discussed enough of this formalism that I can connect up to what he said, to what he discussed, and things will be somewhat clear. So let me sort of show you how so say I have a Hamiltonian in 2 dimensions. It's a Floquet Hamiltonian, so it's time-dependent, periodic, and it satisfies this MBL property. Okay, so for such Hamiltonians, I'm going to show you how to extract a quantized invariant. So in other words, such Hamiltonians with that property don't all sit in the same connected component. It turns out that there's an inner quantized invariant which distinguishes them. And here I'm assuming my system is built out of qubits. Okay, so there's more fancy things that can happen if you have Q-trits in different dimensional local Hilbert spaces, but I'm just going to be working with qubits. Okay, so let me show you how to extract a quantized invariant from a 2D Floquet MBL Hamiltonian. So let's just write down what we have. So we have a Hamiltonian that's a sum of local terms. Okay, so these are local terms, and and I can form the Floquet evolution, which I already wrote down, but let me rewrite it here. Tx I 0t h of t dt. Okay, so this is all in 2D, and so the MBL property says that there exists finite depth circuit of local unitaries. Let me call it V in this case, just because I'm using U for the Floquet, such that such that by conjugating by this circuit, finite depth circuit, I can put the Floquet evolution, the Floquet unitary. There's not supposed to be a dagger here, into this MBL form, e to the minus I t times h MBL, where h MBL is, remember, where h MBL is of this form that basically has, let's say in this case, Pauli z's as conserved quantities. Okay, so sum of hi prime zi plus jij prime zi zj plus all the other terms that you can build out of z's, local terms that you can build out of z's. The important thing is that it just has z conserved quantities. So this thing looks kind of boring. There's certainly no, the eigenstates of HMBL are really boring. They don't have topological, or they don't have anything. So how am I going to extract a quantized invariant? Well, this turns out to relate to what Matt was talking about, looking at a circuit as a path in the space of unitaries. Okay, so this Floquet unitary U sub f is a circuit, and it's not really a circuit. It's a circuit with tails. I'm going to sort of gloss over all these distinctions for the purposes of this talk. But it turns out there's information contained in the path through the space of unitaries. If you just imagine, sort of not just considering the evolution up to time t, but the whole path, the so-called micro motion of this Floquet system, from 0 to capital T. And so to formalize that, let me basically, let me do the following. Let me truncate everything. Okay, so implicitly here, this V exists. This thing that diagonalizes this Floquet unitary exists either in infinite system size or a finite system without boundary, maybe with periodic boundary conditions. But boundaries can screw this up. So let me do the following. Let me truncate the Hamiltonian. So only keep terms within some region A. Okay, so I'm just going to. So this is my region A, and I'm going to truncate the Hamiltonian and call it H sub A. So I'm just keeping the terms, the local terms inside A. Again, this is time dependent. And that from that, I can construct a Floquet evolution that's just evolving inside this region A. So in other words, it's just the Floquet unitary built out of this truncated Hamiltonian. Okay, so so this is time-ordered exponential of 0t ha of t dt. Okay. Okay. So I think the rest of this I'm just going to say in words since I don't have too much time left. But the essence of this is of extracting this quantized invariant is as follows. So remember that. The original Floquet unitary, the one that let's think about an infinite system size or periodic boundary conditions, can be put into this form. So in other words, it has local conserved quantities. If you conjugate these z's, which all should have hats on them, by v or by v dagger, then these are conserved quantities. These commute with the Floquet, the sort of untruncated infinite size of Floquet evolution U sub f. So because U sub f is basically a finite depth circuit with tails, and V is a finite depth circuit, if I just truncate U sub f and I truncate V all into this region A, and I imagine just taking sort of the truncated version of this equation where I replace both V and U sub f by their truncated versions, then deep inside the bulk of A, so somewhere in here, sort of far away from any sort of length scales associated with the depth of the circuit, this should precisely look like the untruncated version. So in particular, deep inside the bulk, the truncated Floquet evolution has conserved quantities. Okay, so deep inside the bulk, this thing is frozen. Deep inside the bulk, this truncated Floquet evolution just does essentially nothing. I mean, doesn't do nothing, but it has local conserved quantities. Okay, so you can just kind of freeze it in place by looking at eigenstates of these local conserved quantities. But it turns out it does something non-trivial on the edge. Okay, so it turns out that this local, this truncated Floquet unitary, there's no guarantees as to what happens near the edge. Okay, there's no guarantees as to what happens near the edge. The only guarantee is that it's some kind of a locality-preserving unitary. So locality-preserving, it certainly preserves locality because it comes from it is a 2D finite depth circuit. But so the idea is that you can extract the 1D locality-preserving unitary by kind of freezing the local conserved quantities in the bulk. So they're sort of frozen and out of the game. And I don't have time to sort of formalize that. But essentially, the idea is that you can extract a 1D locality-preserving unitary. And so the point now is that this 1D locality-preserving unitary might precisely have one of these GNVW indices, non-zero GNVW indices. And so that would be a non-trivial chiral Floquet phase. Okay, so that's all very abstract. So maybe the thing that I'll sort of end on, maybe the picture that I'll put up is a particular example of this. So this was actually sort of, people came up with this in the context of free fermions. And we sort of generalize it to interacting systems protected by MBL. But there's an explicit example of such a Floquet Hamiltonian, of such a periodic time-dependent Hamiltonian, which does precisely this, which kind of has frozen local conserved quantities in the bulk and implements this non-trivial QCA at the boundary. And that's shown in this picture here. So this was sort of what Matt referred to when he talked about paths in the space of finite depth circuits, or I guess he want to refer to it just as a finite depth circuit, relating that in 2 dimensions to QCA in 1 dimension. So the idea is that somehow the degrees of freedom in the 2D bulk kind of dance around in this way, but they all come back to their original position. So the Floquet unitary, which only probes the system at stroboscopic times, doesn't see that micromotion, but something non-trivial happens on the edge. So the idea is that it's basically this Floquet evolution here. So the idea is that for the purposes of what I'm talking about, you can just imagine these various colored segments as swap gates, so unitary swap gates, which swap the qubits living on these various vertices. And so the idea is that if you implement these swaps in 1, 2, 3, and then 4, you kind of have to sort of play around with this and convince yourself that in the bulk, everything just goes around a little square and comes back. So the full Floquet unitary that you build just is the identity in the bulk. But on the boundary, things get translated. Okay, on the boundary, this is a translation with sort of GNVW index, the lowest non-trivial GNVW index. It's actually kind of non-trivial. It's like half. It's not like each site on the boundary gets translated by 1. Half of them are fixed, and half of them get translated by 2. But that's stably equivalent to just a translation by 1 on all sites. Okay, so I think I'm out of time mostly. So I think what I want to just end with is that good timing. It's sort of good to think about the various physical contexts in which you can realize some of these different mathematical structures. And QCAs in particular, can very nicely be applied to these kind of MBL protected Floquet phases, or more general non-equilibrium phases. So that's one very nice physical application of QCA. There are other applications of QCA for equilibrium SPT phases, and I think that's going to be related more to what Zhengwen's going to talk about later today. But yeah, let me just end here. Thank you.